In this session, let's look out for this two-state Markov model used very heavily in the insurance world, where there are only two states, which are typically the alive and the dead state. Right? Generally, when I am looking at between the alive and the dead, okay, there is only one transition between these two states. At some point in time, a person who is alive will with some particular age, right? Probably if I am assuming that X is the age of the person, at some particular point in time there is a transition to a death state, and probably the force of transition, here we'll define one word called the force of transition or the transition rate, right? Transition rate is what we denote by mu x. Generally, this mu x is assumed to be constant within 1 year. Assumed to be constant during a 1 year period. So probably whether he die, whether the person is aged 55.5 or 55.7 or whatever it is assumed to be constant during a 1 year kind of a period. So one thing is, in a two-state Markov model, we are more looking at a person being alive moving to a death state, right? Whatever depending on his age x. So x is the age of the person. So when I say mu x, the the force of intensity or force of transition, probably a person who is generally people at very high age, let's say 75 or 80, the force of transition to death is very high because more number of people, there's a good chance of dying. But probably for a person with age 30, the force of transition could be much lesser. So that's the reason why we say the force of transition is based on the age X. So that's where sometimes this force of transition is also being called as force of mortality, the chance of dying, or even typically the hazard rate, right? It's just not it need not be something that is associated only to the insurance world or person living versus dead. Even a machine, alive versus dead, the age of the machine versus the machine going into a non-usable kind of a condition. All these things do come up as a part of this two-state Markovian model. But the only problem difference there, at least in this kind of models, there is no possibility of reverting. A person who is dead, he cannot go into the alive state, but a machine which is unusable may go back to the usability state. So there's a slight difference from that particular dimension, but the plainest of the mechanism is something which is in the alive state going into the dead state and not coming back to the alive state at all. So here we are defining two important terms, TQX and TPX. This means a person currently aged X, right? Or the person currently aged X. What is the probability of dying by the time he reaches X plus T years, given he is alive at X? What is the probability that a person aged X dies by the time he reaches X plus T? This is what is the TQX we talk about. but the opposite of it, the person alive at x plus t given he is alive at x. So given that the person is alive, so whenever I am writing it toward this side for p or q, person is alive until that particular age. Now if I write it as q, I am trying to find out that what is the chance he will be dying. If I write it as p, it is like what is the chance that he will still be surviving. So that's where this is called as even the survival probability. What is the chance of survival for the next t years? A person who is currently aged x, what is the chance that he is going to survive for the next t years? Whereas the person is x, what is the chance that he is going to die in the next t years is what we call as transition probability, because we are talking about transition from a alive state to a dead state. Whereas this, so probably if I am looking at these two boxes, see alive and dead. So this is more to do with the transition, whereas this is more to do with survival. So within this particular point in time, for a person who is currently aged X, what is the chance that he can survive for another T years, and what is the chance that he is dead within the T years? So that's the reason we generally start writing TQX as 1 minus TPX, because the summation of these two should be equal to 1. Chance of, see, for a person who is alive at X, chance of he dying in T plus X, or he is alive by the time T plus X. So the summation of those two probabilities should be equal to 1, which means I can write this expression as the relationship between the two. And one more important point which I should like to look out here is the same TQX. Sometimes if I want to find out only within the next 1 year, what is the chance that a person is X will die in the next year? So it is like 1QX, or sometimes we ignore the 1 and we'll write it as QX. When I say QX, the probability that the person will die in the next 1 year, and the corresponding px is the probability that a person aged x will survive for the next year, right? So that is one more dimension to typically look at. So first of all, for this kind of a model, one, we assume that it is a Markov model. Why? This is a Markovian model because the probability of occupancy of any particular state, alive or dead, it is purely based on the current state, depending on whether he is alive or dead, and along with the age. For each age, probably there is a different probability of transition, but the probabilities are purely dependent on the current stage itself. And this also makes another important assumption. When I take the H as a very small time period, a person who is currently aged some x plus t, a person who is currently aged some x plus g, what is the chance that he dies within the next h period? H is a very small time period. For H is a very small time period, then probably it is coming out as this. I can take it as H multiplied by mu x plus t. The force of transition, because we are talking about it as a continuous transition probability from alive to dead state. So I can take this as H plus H multiplied by the transition probability or force of transition mu x plus t plus some small adjustment for this h. This is one more important thing that we have to look out. The relationship HQX plus T, a person who is aged X plus T, dying within the age X plus T plus H, where H is very, very small, I can take it as based on the transition, the force of transition during that period, which actually during a small period of 1 year, the entire mu x plus t is taken as a constant itself for the entire 1 year. So probably between 56 and 57 years, the mu x plus t is typically treated as constant itself. Between 81 and 82, the chance of dying within the next 1 year is being treated as constant for this period of 1 year altogether. So going with that kind of an assumptions, right? For this model, we generally make these three assumptions, and going with that, probably if you want to look out for a person who is currently aged X, surviving for T plus H period. So what I'll try to write it is, okay, currently a person aged X, what is the probability that he will survive until X plus T, which is TPX, and a person who is aged X plus T surviving until the period H. So this could be the expression I can write. T plus H Px, first surviving up to T period, and by that time his age will become X plus T and surviving for one more H period. So this probably I'll try to write it as Tpx, and this one I'll write it as 1 minus HQX plus T. And we have made a relationship here, HQX plus T. So I can very well write it as Tpx minus Tpx multiplied by HQX plus T. I'll write it as H into mu x plus T. Right? So now doing a small arithmetic, T plus H Px minus Tpx, right? T plus H Px minus Tpx is equal to minus Tpx H mu x plus T. Fair enough. Now I take this down, minus Tpx. This becomes H into mu x plus T. Logically speaking, this is nothing but, probably if I keep the minus here itself, T plus H Px minus Tpx divided by, instead of dividing by Tpx, let me divide it by H. So here there is minus Tpx. Okay, so this is nothing but the derivative. The definition of a derivative is nothing but f of x plus h minus f of x by h. So the same logic if I am talking about here, this is nothing but d by dt of Tpx. So this is coming out as minus Tpx into mu x plus t. Now I'll bring this Tpx down. D by dt of Tpx by Tpx is minus mu x plus t. So whenever we are talking about a derivative, right, probably this is looking like f dash of x divided by f of x form. This is nothing but f dash of x divided by f of x. So this I can very well write it as the f dash of log f of x. If ever I am seeing this kind, I can integrate these two and write it as f dash of log f of x because log f of x, if I am taking, it is 1 by f of x, and the derivative of 1 by f of x is f dash of x. So it becomes f dash of f of x, f dash of x by f of x. So this I will write it as this. So this is equal to minus mu x plus t. So I'll remove this derivative. So which means I am doing an integration now, right? I'll do this. I'll remove this derivative. So I'm doing an integration. Log tpx is equal to integral between some part, let's say 0 to n minus mu x plus t. So tpx is nothing but, I'll take an e to the power of minus 0 to n mu x plus t dt. So this is what will typically become, right, will typically become 0 to n mu x plus t dt. So this is what is the expansion of, so probably I could write in a better way, tpx e power minus 0 to t mu x plus s ds. Means the probability that a person is aged x will survive until another t years is nothing but e to the power of minus 0 to t integration mu x plus s. Probably it is looking more like a present value kind of a formula, e power minus integration of force of interest. So the same logic is going for your survival probability. If we see, there is a lot of resemblance between these two. When we talked about the present value, we simply said of any present value factor, we said integral of 0 to t delta s ds. So here also survival probability e power 0 to t mu x plus s ds. The force, this is a force of interest, this is a force of transition. So the force of, based on the force of transition, I am trying to find out the present value kind, which is nothing but the survival probability. So I can take the survival probability as e power minus 0 to t mu x plus s ds. Now, obviously, if based on the assumption that within a period, within one period, mu x plus t is mu x plus s is constant. So probably for a t year period, assuming that constant kind of a probability, for a survival up to t years, if I want to know, this can get updated to e power minus mu t directly. If I am talking about a uniform within a 1 year kind of a period, then probably tpx is something I can take it as e power minus mu t directly. So this is a way that we can derive the survival probability. Now, in this, so how do I define, how do I find out this value of mu, especially from the observed data? From the observed data, how do I find out this mu? So for that, all we are saying is, let's say during a time period, so the process now, let's see, during a time period, I started observing so many people, so many lives. Probably from this period to this period, between these two times, I started observing so many people, right? When we start observing the people, okay, they are all alive at this moment. But probably some people may die by the time they reach somewhere here, right? So there could be a kind of a die that can occur. And at the same time, some people, their information will not be available after a certain point in time. So we are calling them as censored. See, if they die before my observation period getting closed itself, there is one possibility, and they could even get censored before they die. Means their information is unavailable to us and all. So now if I have to do the prediction for mu, if I have to do the prediction for mu, in general we use the observed data and then we follow the approach of maximum likelihood. We follow the approach of maximum likelihood to determine this mu. So out of the lives which we are observing, right, some of them can die. So probably if I am saying this is A and this is B, so the overall period of observation is B minus A. But within this period itself, we see some lives dying, we see some lives getting censored. So we are more interested in finding out what is their contribution to the likelihood for each one of them. So for a dead person, the contribution to the likelihood, right, probably a person, look at if a person is dead, TQX, right, so probably it's like if I'm looking at, I'm observing a person who is aged X, so probably if I have to find out a person who is currently aged X, I started observing him from X plus A, but probably by the time he reached X plus A plus B, he is expired. So this would have been written as, okay, a person just surviving up to this X plus B, X plus A plus B, and then getting into the force of transition, reached the X plus A plus B, and he has actually gone into a force of transition kind of a state. Now this actually becomes, if we see, this part is e power minus mu. This is e power minus mu and the time period for which we have observed this person, B. The time period for which we have observed this person, so this becomes e power minus mu B, because TPX, we got the formula as e power minus mu T. So here I will write it as e power minus mu B into, so this during this 1 year period we say this is constant. So a contribution of a dead person to to the likelihood equation is this much. But look out for a person who is alive. So for this B period, we are talking about a person who is alive. So this actually becomes BP X plus A direct, which means it just becomes e power minus mu B. This becomes only e power minus mu B only. So if there are some d number of deaths that have occurred during this period, right, out of all the people which I have observed, let's say there are d number of deaths, then what is the maximum likelihood function here? The product of what is the likelihood function here? The likelihood function is the product of all the corresponding probabilities. So for the dead people, mu power d into e power minus mu b to the power d. This is what is being contributed by the dead people to the likelihood function, right? And Similarly, what about the weighting? Similarly, what about the alive people? Again, there are mu b, e power minus mu b, and whatever is the number of alive people. So probably n minus d is the number of alive people. So these are what are the total contributions, right? E power minus mu. So again here the b may not be constant for all the people. Either they would have got censored at a different point in time. So probably this would have become, okay, this is mu power d, but this would have become e power minus mu b1, b2, b3, so on. So this would have become actually b1 plus b2 plus so on up to bd number of people, and this also would have gone e power minus mu, again the different time periods associated with them, right? So this will become my likelihood kind of a function, mu power d e power minus mu into the summation of all the dead as well as live kind of people. So now what we are simply saying is, if I'll try to find out the log likelihood. The log likelihood, probably if I am writing this particular multiplication as the likelihood function for mu, I'll try to find out the log likelihood function for this mu. The log likelihood is when I am taking the logarithm, okay, d log mu minus mu times, okay, the total period which I am observing. So let me call that as the total observation period, b1, b2, b3, b so on, and even when the people are moving out, whatever is the periods at which they are moving out. So the log likelihood function is coming out to this much. Now I'll do the differentiation with respect to mu so that I can estimate the mu better. So this comes out d by mu minus b. Mu is, so this first derivative I'll find out and equate it to 0. So I get d by mu equal to v, and from mu I get it as d by v. D is nothing but the number of deaths that are observed during this observation period, this divided by v, time period of observation. I am not saying number of people observed, time period of observation. So probably in terms of months or in terms of whatever is the smallest period we can think of. This is an estimate for mu. The estimate for mu for me here is the number of deaths observed divided by the total observation time during this period. And okay, try finding out the second derivative for the same d by mu minus v equal to 0. D by mu minus v was the first derivative. So minus 1 by mu means minus 2 by mu squared, right? Minus 1 by mu squared. So minus d by mu squared. So mu squared is positive, d is positive, so this overall number is less than 0, which means this is the maximum value itself. So whatever the value that d by v got generated, that is what is the maximum likelihood kind of a value. So the better estimator for mu is d by v. And if at all I want to know what is the variance, right, whenever we are talking about a simple two-state model, first of all the better estimate for transition from one state to another state is based on the observation. Find out what is the total observation time, and within that observation time how many deaths have got registered during the period, or how many transitions have happened during that period. Based on that you should be able to compute what is the better estimate for mu. And if I want to find out the the confidence interval part, we know asymptotically we see that maximum likelihood estimators, they follow a normal distribution with the mean as well as the mu squared by expected value. That is what is the typical estimation with respect to this maximum likelihood estimators. So probably I can say that it follows a normal distribution with mean. Here mean for me is d by v. So mu square is d squared by v squared and divided by estimate of d, again probably I can take it as d itself. So it becomes a d by v squared. So it takes as d by v as the mean and d by v squared as the variance. So by computing d by v as well as d by v squared, because this is nothing but mu and mu squared by d, I should be able to find out I should be able to find out from mu and the actual number of deaths. I should be able to find out mu square by d, and based on this I should be able to talk about the 95% interval, which is nothing but I take the square root of it, mu plus or minus 1.96 times square root of mu squared by expected value of the death. So this is what will become my 95% confidence interval for mu, which can very well be used to estimate, which can very well be used to find out the transition probability, the worst case as well as the best case kind of transition probabilities. So in a two-state model, things become more and more simpler by doing this kind of approaches. Just by knowing this mu and we can find out the transition probabilities and all these things. So what we can very well do is we'll take up numericals, a couple of numerical practice questions to work out these kind of relationships so that a clarity gets developed on the same. Alright. With that as a base, let's start jumping into the numericals and start working out on those numericals associated with the two-state Markov model. Alright.